Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we'll be using the direct comparison test to deduce something about the convergency or divergency behavior of the infinite series. So what is a direct comparison test? When you're given two series having an inequalities in between, for the n terms, like for example an and bn. So in this case, an is less than or equal to bn for all n. So if you know something about bn, especially if it converges, like the series bn converges, then the series smaller than that has to converge, okay? Or if you know that the series an diverges, and the series Bn is obviously greater than that, so that has to diverge as well. So when is the best time to apply the direct comparison test? Well, if you know that you can compare the given n term to another one, so you should construct an inequality between the n term given to you and the n term that you know the behavior of, and then see if you can prove the first or the second item for the two series. So it's a very specific test, and it's very special to apply this test to certain infinite series. So again, you're going to gain this experience by going over more exercises, because we are sort of like piling up different tests to be applicable for the infinite series. But it's your judgment at the end of the day to see which test is the best to apply to the given infinite series. But since we're learning the tests at this moment, so the test that we're going to use is given in the problem, like in this problem that it says use the direct comparison test to prove the convergence or divergency. But anyway, so we're given three infinite series. We have a long way to go. So why don't we get started?
All right, let's start with the first infinite series. That's 1 over n cubed plus 1. So in direct comparison test, we got to compare, let's call this 1 over n cubed plus 1 to be an. I got to compare this to bn. But the question here is that who is bn? And once you have bn, so would you have this kind of like inequality between an and bn? But staring at the expression 1 over n cubed plus 1, I can see that this an for larger n is behaving like 1 over n cubed, because when n gets larger and larger, the contribution of 1 to the bottom is very minor, right? Just think about like larger n's. So for that reason, an being like 1 over n cubed plus 1, bn could be 1 over n cubed, because again the contribution of 1 is not major. But the question is like, can I prove that an is less than or equal to bn? Well, it is the case, because 1 over n cubed plus 1 has a bigger denominator than 1 over n cubed no matter what n is. So in other words, 1 over n cubed plus 1 is always less than or equal to 1 over n cubed for n greater than or equal to 1. So if this guy is an, if this one is bn, here we go. I have this inequality to hold true. And in fact, the better news here is that I know a lot about the series 1 over n cubed, okay? Because if there is inequality like that, but I add the sum, infinite sum here, nothing is going to change. The infinite sum here, if it's convergent, okay, this infinite sum here is going to be larger than this infinite sum here, okay? Again, what do I know about this infinite series? Okay, well, first of all, it's a known type of series. It's P series, okay? It's P series, and 1 over n to the power of 3, so it's a P series of P equals 3, and which is greater than 1, okay? That's good, because P series for P greater than 1 is always convergent, okay? So look at item number 1 here. It says like if the series Bn converges, then the series An converges. So if this guy here is less than infinity, so that means it converges to a finite number. The sum converges to a finite number. The sum smaller than that, which is this one, right? has to converge, right? Because this second series on the right becomes a bound for that, and that bound is a finite number. So in other words, let me just clean this to show you the bigger picture over here. So let me just clean that. So we have this inequality to hold true, right? So, and I just said that this is a p-series. The one on the right is a p-series, so it converges. So here we go. If it converges, this sum is less than infinity. Okay, well, this sum is already less than something convergent, so it has to converge. Okay, so here I can go back and conclude that this is a convergent series. Okay. All right, at this moment, I'm gonna step back and then get some visuals for part A and part B. So we had two infinite series, 1 over n cubed plus 1 and 1 over n cubed, and we just proved that 1 over n cubed is less than 1 over n cubed plus 1 is less than 1 over n cubed. Okay, so the purple one and the red one, as you see, purple one is 1 over n cubed, and 1 over n cubed is a convergent series because it's a p-series, and it converges to this number here. As you see that the one smaller, the red dots here, is representing the series given in the question. So that is smaller than the series 1 over n cubed, and 1 over n cubed is convergent, so this has to converge. Okay.